Alright, good morning guys. Look what I have found. It is the paper one from yesterday from Edexcel for A-level maths. So I've done this all last night. I've checked it all last night and I think I've got everything correct. I mean, it all worked out on Desmos when I looked at the graphs and on wolfram alpha and stuff. It all calculated correctly. So I will go through and show you every answer, and I'll put at the end just like a quick run through of all the solutions as well. So I've checked it every single thing basically. There's one or two bits I can't check, like the proofs, do you know what I mean? Some of the bits as well where they've got just all algebra going on, like this one, there's no letters and stuff, it's hard to check. But I think everything looks good. Everything kind of works out nice and straightforward. Maybe not straightforward, but everything does seem to work out. Let me remove that one quickly. So we will go through from question one all the way through. If anything looks wrong, please let me know. This is only me doing it myself, so I've got no guarantee this is correct, but I think this is right. And also I can only go on what's written here. So if this is not the exact question, it might not be the exact answer you got in the exam, but it should be the same sort of method if the numbers are slightly wrong. So first, we've got some point on a curve. It's been mapped with this transformation. Same thing down here. What these transformations do, so the 2x in the bracket, that's an enlargement in the horizontal axis by a half, and the 4 outside it is an enlargement in the vertical axis by 4. So the y value will be times by 4, so that 5 becomes a 20. The x value is times by a half, so minus 2. Similar thing for the next one then, but that 3 is taking us left by 3. The 2 takes us down by 2. So not enlargements, but just literally translations, just sliding the point across. So if we're at minus 4, we go left by 3, we should be at minus 7. We're at 5, down by 2, we should be at 3. I have got my answer key next to me, so I will double check all of these, and that's the same as what I put yesterday, so that's a good sign. Part 2 then, we've got an equation. We want to show that this has a single root alpha between 1.1 and 1.2. The equation is over here. So just nice and simple, plug in 1.1, 1.2 into both of these bits. When you write down the calculator, we get numbers of, so for 1.1, we get negative 0.3799. For 1.2, we're going to get 0.6552. So you can see we've got one positive, one negative. How did it change between those two values? It must have either crossed 0 or it's had an asymptote, like gone to infinity and then come back round again. So what we have, f is continuous on the real numbers, and that we have the product of f1 and f at 1.1 and f at 1.2 is negative. This is just a way of saying one's positive, one's negative. If you times them together and you get a negative thing, one must be positive, one must be negative. Could be the other way around, but one must be one of each. So those together, what we have is that alpha is in between 1.1 and 1.2. 1.1 and 1.2. Looks good for me. Iterative formula, just plug in the numbers. We've been given the formula, x is 1.1 to start. The first one, I got 1.1542. And then the value for alpha to 4 decimal places, just keep whacking equals. Put this in, answer for this bit, do you know what I mean? Keep whacking equals till it comes through and settles. What we got was 1.1384. And if we look at the graph of this thing they've given us, it does cross at that point. If you look at the decimals, that is where it does cross. So that looks correct for me. Everything on this page is matching what I said yesterday. So these should be the correct, if these are the actual questions you had. We'll keep going. Put something to differentiate, find dy dx, simplest form. X cubed, 3x squared. 2x squared becomes 4x, plus 5x becomes a 5. Is that the same as yesterday? Yep, looks good to me. We're going to find the tangent to the curve where x is 2. Give your answer in the form of y equals mx plus c. So first thing, we need to find not only the y coordinate, but also the dy dx coordinate. So let's plug it into both values. Y of 2, what does that give us? So we get an 8, minus an 8 cancels out. There's a 10, take away a 7, gives us a 3. If we then also plug it into dy dx to get the gradient at that point, x equals 2. What do we get from there? So we're going to have 4 times 3 is 12, take away an 8 is 4, plus a 5 is a 9. So we've got a y minus a 3 is equal to a 9 times by x minus 2. Expanding these brackets, how many x's do we get? 9 over there. For the numbers, minus 18 plus a 3 gives me a 15. So I get y, 9x plus 15. And is that the same as yesterday? Yes, it is. Oh no, I got a minus yesterday. Oh yeah, ignore me. It should be a minus. That was a minus 18, wasn't it? Plus a 3, minus 18 popping out. There we go. That looks good to me. And again, if you plot this graph, if you put in point 2, you get the gradient function at that point. It is this curve. It is that exact curve. This is the tangent. Everything does work out correctly. So let's keep going. Range for f, you can probably see it's just bigger than -2. If you want to write it in the kind of full way, we can start with a known fact that we have that x is all real numbers. So that's going to tell us that x squared is always positive. Could be 0 as well, so it's always non-negative. So if we were to triple that, tripling something will not change its negativity. And if we take away 2 from both sides, 0 take away 2 is -2. And now you'll not spot that thing is f. So f of x bigger than or equal to -2. Again, you can just see that from there straight away if you want to, but no harm in practicing how to do this sort of stuff. GF of 2. So we'll plug in 2 into there. What we're going to get, 4 times 3 is 12. Take away 2 is a 10. Plug it into there. 50 minus 1 is 49. 49 on 10 minus 4 is 6. So 49 on 6. So 7 squared. No cancelling happens there. And that's the same as I got yesterday. And again, I've checked both of these on Wolfram Alpha. They do pop out giving you this value. The inverse, a few ways you want to do it. I'm going to say that y is equal to 5x minus 1 over x minus 4. I will times the x minus 4 over. So I've got xy minus 4y equals to 5x now minus 1. Now I start with a single y, so I want to end up with a single x. So I bring all the x's to one side, all the y's to the other. If I bring this over there, I get positive numbers, and I bring that over, I get negative. So it doesn't really make a huge amount of difference geometry we go here, because we've got one of each negative, positive sort of style thing. So I'm just going to bring all of my x's to the left. I have xy minus 5x is equal to 4y minus 1. Let's just move that left a little bit. So if we can factorize for the x and divide, x would be still 4y minus 1 on the top. The bottom will be the y minus 5, the left-hand side. And then this thing is the inverse of g. We just need to swap those x's and y's around. What this thing is the inverse of g, just of y. So I think you had y equals g of x, is what you started with, and you rearrange, so inverse both sides. Inverse g of y is equal to x. So that is what you technically end up with, hence why we're going to swap them over, and then it's like, okay, x and y just swap places. And that's why the reflection is the kind of transformation that you see. So looking at that, 4x minus 1 over y minus 5. And again, I did check that online with the calculator, and that is the correct inverse there. If you sub this back into the original one, you get out just x. So that's all good. Spot on, that looks okay to me. Let me just double check that is the same. Obviously, notice the little letters changes. This should be an x, not a y. Do be careful of those things. You're never going to completely stop me from doing that. Do you know what I mean? I've done maths for 26, 27 years now, and I still do these things every single day. You just need to learn how to check yourself and catch yourself when these things do happen. Let's keep going. Number 5. Number 5 made me laugh, because if this is the flight path of a helicopter, I would not be getting into it, because you're going to go so far and then very quickly you're going to just dive into the ground. So do not do this if you're a helicopter pilot. Do some other flight path. But yeah, we have this. X is the horizontal, y is the vertical, t is the time, obviously it's taken. Write down, according to the model, the maximum height. Well, height is given by y. Sine, no matter what we put inside it, it's maximum 1, times it by 10, max of 10. So max height is 10. Find, according to the model, the horizontal distance the helicopter has travelled from the origin when it's 5 meters above the ground for the second time. So we need to solve that y equation. So the 10 of sine t squared on 4 is equal to 5. So doing that, we'll divide by the 10. We're going to have sine of t squared on 4 is equal to a half. So if we do inverse sine of a half, what do we get? Well, the first solution is 30 degrees. The second solution is 150. So when we work with this, we need to work with 150. Do you think that helicopter's been on the ground, it's gone up, got to 5, carried on going to 10, turn back around, hit 5 again, and then it will just nosedive. it will just fuck this, let's just die. So we're going to stop it before it dies, basically. We're going to say to stop at 5 meters or something. So let's now plug this value back in. Not plug in, sorry. Let's work out the time. So to do that, we need to set the t squared on 4 equal to 150. So doing that, t squared will be 600, and therefore t is the root of 600. I think I just left it as this in my answer, but I did get decimals out. What did we want? Horizontal distance. So now we have that time, we just plug it back into here. So it's going to be x is equal to 100 times by the square root of t. T is already square rooted, so we need the fourth root. So it's times by 600 to the power of a quarter. If we get decimals for that, what was it? I'll just double check it is the same. 100 times 600 to the power of 0.25 to the power of 0.25. I get 494. Was that what I said yesterday? No, yesterday I said 179. I think the difference in the radians and degrees. This is 494.9. Let's follow the same thing through with degrees. What happens? Sorry, with radians. The 150 is 5 pi on 6. So this is now the square root of 4 times that, because we times this by 4. So it's going to be 20 on 6 or 10 on 3. Lots of pi. And that is all square rooted. And again, this would now become the fourth root down here. So this would change to 100, 10 pi on 3, all to the power of 1 on 4. So if we use that one, what do we get? 100, lots of 10 pi on 3, all to the power of 0.25. I get 179.9. So either one of these could be correct. At no point in the question I've got here did it specify, I don't think. And we haven't done any differentiation or integration, so there's no reason to, there's nothing here that's saying we have to use one or the other one. So both, depending on which answer you use, I don't think they'll mark you down. And if they haven't told you, they shouldn't mark you down. Do you mean? If they told you to use one, they will obviously mark you down for it. But both of these should be completely fine. That looks good to me. And that is the same number, yeah, 179.9, same as yesterday. So that's good. Find this thing. This is reverse chain rule. It's the log thing. So what we need to spot is that when you differentiate 7x, or 7x plus 1, you get 7. So we really want to write this where we have 7x plus 1 on the bottom and just a 7 on the top. How do we do that? Well, we had a 3 there, so let's put the 3 out the front. And then we've had to times by 7, so we need to divide by 7 as well. So we get 3/7 of this thing. This still has the dx line around. And performing that then, 3/7 of this is log. So 3 over 7, what's the natural log of the thing on the bottom? 7x plus 1. Always remember, if you have a function and its derivative on the top, it's the log of that derivative. And as always, we need to add on our c. You can put anything you like at all. Doesn't have to be a c. So now looking at this, I've assumed that this is not 2 to the power of p times this stuff, and then you're doing things. I've assumed this is limits. I didn't walk through the other way around. I don't think it works the other way around because you won't have the limits. You'll just have an expression that needs to always equal a number. So I don't think that's possible in that case, but I haven't looked if it is possible. But if we do it with the limits, you can see the question is very similar to the one we had before. We've got p and 2, and then it's the same thing, 3 over 7x plus 1. So we know that this is the same as what we have above. It's the 3/7 of log 7x plus 1. We just want to sub in those limits of p and 2, and then set that equal to the 6/7 we have above. So that's looking good. As we go and do this then, let's sub these bits in. 3/7 I'll take out the front, leave that alone. You could deal with that with the, actually yeah, let's deal with that with the 6/7. So the 7ths could just go. We don't need those. This is 6 divided by 3, it's a 2. So this whole thing will equal 2. And then let's plug the limits into the log part. So 7p plus 1. So we have log of 7p plus 1. Take away the log of 7 times 2 is 15, plus the 1 is, sorry, 7 times 2 is 14, plus the 1 is 15. So we have that. Let's combine the left-hand side into one single logarithm. So we've got the natural log of 7p plus 1 over 15 is all equal to 2. And then let's raise both sides to the power of e. So 7p plus 1 over 15 equals e squared. And then rearranging this for p, what we have is that p is 15e squared minus 1 over 7. Is that the same as I got yesterday? What question are we on? 6. P squared. P is, yeah, 15e squared minus 1 over 7. Yep, spot on. And again, I did go and check this. When you use that as the upper bound for this, it does give you exactly 6/7. So this is all looking good. Should be completely correct. Let's keep going. Number 7. Yeah, this one. Whoever made this paper, you've labeled everything correctly. Like whoever made this like copy of it, Jimmy, has labeled this correctly, but B should be on the other side. If you're thinking what it says down below, we have that the area R1 is twice that of R2, so R1 must be bigger. So you've labeled everything correctly, but like this one is just be a mirror image. I mean, that one should be over here somewhere. Does make a huge difference actually how we're going to work with things. You can basically just ignore that and not worry about it. We want to show it satisfies this. I did double check, like, have you just labeled things the wrong way around, maybe? But if you do it the other way around, the initial thing you get has a single pi, and you have to double everything. The way around you've got up, like the labeling you've used, it gives you exactly a 2 pi. So I assume the labeling that's been used here is the correct one, but the other way around is not too dissimilar. It's just like one bit, we just have a 2 on a different side of the equation. So let's look at this. Let's work out the areas of R1 and R2 individually. They're both very similar. So what we can do is just use the area of a segment in general. So area of any segment is the area of the sector. Take away that triangle that we have. The general segment sector formula is r squared theta on 2. And the triangle formula is going to be a half r squared sine theta. So very similar, but theta is now sine theta. So I will factorize that out. In general, we have r squared over 2 multiplied by theta minus sine theta. So that's the general equation. That is actually R1 in this case, like because R1 is just using all the general numbers. But R2 is slightly different because we don't know what that is straight away. But we do know that it must, alongside theta, add up to pi. So it is pi minus theta. So using that, we're just going to swap over those thetas. So still r squared on 2, but the theta is now pi minus theta. And the same inside that sign, pi minus theta. So now we have two expressions, well, an expression for R1 and an expression for R2. Before we go on, deal with this. If you want to expand the brackets and rearrange it, that's completely fine. It's okay to think about this in terms of transformations as well. Let's ignore that negative. What's happening here is we're reflecting it in the x-axis and then shifting it by 180. Well, every time you shift it by 180, it is like the negative of itself anyway. So what this thing is, it's just exactly the same as sine. It's just sine theta. There's no difference between that and sine theta. You'll get that as well if you like do the the compound angle formulas, doing expand everything out. It will just be the same as sine theta and just matching the sign above. So yeah, they are identical. They work for every single value of theta. So this is good. We still have that r squared on 2 at the front. And now, yeah, using what they've told us, R1 is twice R2. So this thing is twice as big as that one. The r squares over 2 on both sides. We don't need that here. That's just basically saying that we can scale this up to any size and it still works. So it's scale invariant. So let's set this then. We need R1 to be twice R2. The R1 bits are theta minus sine theta. The R2 bits are going to be the pi minus theta minus sine theta. But we need to double all of those. Pi minus theta minus sine theta. So this is what I was saying about the only change in the labeling that this question is given. If it was the other way around, this 2 is just over there instead. But this one, you can see we get the 2 pi as we expand this out. And that there's 2 pi in the given solution. So for me, that's a sign that everything's looking good. If we rearrange this, we can add pi's or add sines to both sides. So make a sign on that side. Same with the theta, we'll make 3 thetas. So we're going to have 3 thetas plus a sine. And that 2 pi, we'll bring that over as well. So that all equals 0. And that is in the same form they gave us. Let me double check it's the same as I had yesterday. Question 7. Is this question 7? I think I've labeled things wrong on my on my page. Where's this gone? I suppose it's to show that I didn't write it down. But I will double check what it is the same as I got yesterday. It'll be in here somewhere, won't it? Is that it? This one. 3 theta plus sine theta minus 2 pi. So I think that's the same as we had. Yeah, exactly the same. And like I say, yeah, this 2 pi popped out doing this way around, so I think they'd want that. Like, that seems more correct than it being that you've just labeled things wrong and it should be the other way around. But you've drawn it correctly but labeled it wrong, and actually you get a single pi popping out and you double everything. That seems more far-fetched than it just like straight away giving you the 2 pi. It's kind of nice that happened. But again, only given what's told here, this is all correct. This is one that I couldn't really check. Do you know what I mean? It's very hard to check that is the correct answer. Part B of this then. Taking 1.1, expression for theta, apply the Newton-Raphson method. So we need to call that a function. Where was it? We'll copy it down. Should have duplicated. So this is our f of x or f of theta. In general, the Newton-Raphson formula, to get the next approximation, we take the current approximation, we take away its y value, divided by the gradient at that point. What this does is just plots a tangent, sees where the tangent hits the x-axis, that's the next approximation. But doing that then, we need to figure out what is f dash of theta. So 3 theta becomes a 3, sine theta becomes cos theta, 2 pi goes away. So our xn plus 1 formula is going to be xn minus the original, 3 theta plus sine theta minus 2 pi, over the derivative 3 plus cos theta. When we plug in our value of 1.3, we'll get some number out. I will double check this is correct. And again, we've differentiated, so we have to assume radians. As soon as you've got any calculus going on, you need to have radians in your calculator. So 1.3 is the answer. Let's save that in there. Answer, take away this fraction. 3 answer plus sine of answer minus 2 pi's over 3 plus cos answer. I get over 1.73. 734. Is that the same as yesterday? Yes, it is. So it's a good sign. Like I say, if I'm matching yesterday, it's always a good sign. I did double check yesterday's, but this one was hard to check that it is correct. But I think it looks, if you set that in, I think this did. That was where the solution was. All looking good. Let's keep going to number 8. Okay. So this, ignore the faff. I'm assuming again this is like it's not 0 to the power 3. It's just a 3 flying up there in the right place. All of this is just the definition of an integral. So take the bit that you have inside that's not to do with that. So like this bit, and this bit, kind of just say integral symbol. So what we've got left over, x e to the 2x dx. So this tells us it's going to be a dx. And then we have our limits of 0 and 3. So 0 and 3. And now we actually just need to perform that integral. It's a bit harsh, really, because it's going to be like, if you don't do this bit, you've lost 5 marks. It's not a 1 mark question, that. It's a 5 mark question. Because if you can't do that, you can't do this either, can you, really? So, yeah, not quite. I don't know. When we're going to do this, though, what's going to happen? We have a product in there. So it's by parts. Let's call our u, x. U dash is going to be 1 then. V dash will be e to the 2x, and v will be a half of that. So if we call this thing like I or something, there, what we have, I, the integral we're trying to find, must be u times v, x over 2 e to the 2x, when we plug in the limit of 3 and 0, take away the integral from 0 to 3 of u dash v, so 1 times this thing, so a half of e to the 2x. Perform that integral quickly, what do we get? We get a negative quarter e to the 2x. Still got this bit, x over 2 e to the 2x with 3 and 0. And I'll factorise out, makes it a little bit easier to work out what's going on. So I'm going to take out a factor of x, e to the 2x over 4. And what we have then is, how many bits do we need here? 2x. On the end, just minus 1. So it's a little bit easier to kind of work out what's going on. 3 and a 0. So when we put in the 3, we get e to the 6 on 4. That's not very good 4. And this is going to be 6 minus 1 is 5. Times by 5. And we take away 0. E to the 0 is going to be 1. So it's a quarter of minus 1. So taking away a quarter of minus 1, that's going to be the same as adding on a quarter. So if we factorise this out, what do we have? We've got 5 e to the 6 plus 1 over 4. Is that the same as I said yesterday? Yes, it is. Leaving it in that exact form, we'll have 5 quarters of e to the 6 plus a quarter. And that does match up. And again, if you actually go and plug in this, just whack in a calculator wolfram alpha, it tells you the correct answer, and this is that exact correct answer. So that's good. Let's go to number 9. This looks bad. It's not as bad as what it actually is. So I'm going to use like all cos and sines and just c's and s's. So this is c plus s. This is 1 over s minus 1 over c. So as we expand that out, doing FOIL, c over s, negative c over c, s over s, negative s over c. Those ones in the middle cancel out. This is effectively, it's cot take away tan, is what we have there. But we don't want that, do we? We want something different. So let's make this into the same denominator. So I'm going to have sine cos on the bottom. This needs to be times by cos, therefore. So it's cos squared. This needs to be times by sine. So minus sine squared. The bit on the bottom is sine times cos. That's a half of sine of 2 theta. And the top is cos squared minus sine squared. That is cos of 2 theta. So putting those together, we've got a half on the bottom. That becomes a 2 on the top. And a cos over a sine, which becomes a cot. So in terms of like what I'm thinking, just go back to sine and cos, try and just make it into, like, we have 2 bits here, there's lots going on. This has no additions, it's a single entity, it's a single term on that side. So whatever I've started with, if I just make it into one term, this is the correct term, this must be that. As long as I make no like algebra mistakes, then I know that once I've got one term, this is the correct term. And I've got 2 theta in there, so at some point I need to get these double angles appearing, and it needs to be both top and bottom doing. Every single angle had to become a double angle in the end. Looks good to me. Down here then solving it, so you need to spot that this, obviously this thing that we have is that thing. So this is the same question as having 5 times by 2, so 10 of cot 2 theta is equal to 4 cosec squared 2 theta. I know they've used x, I will actually change this to x. This is good. I will divide things by 2 straight away, so that 10 is just going to be 5, that will be a 2. And now we want the, so where you have this is a quadratic in disguise, yeah? I know it's cot and cosec, not like sine and cos or something like that, but it's still the same method. You leave the single power alone, you change the double power. The squared one. So if we have normally that cos squared plus sine squared is 1, let's divide everything by sine squared. You're going to have cot squared is equal to 1, sorry, cot squared plus 1 is equal to cosec squared. So that's good. We have cosec squared here, so we can replace that with cot squared plus 1. So this thing is equal to 2 cot squared, 2 theta, so 2x, plus 2. So just doubling this whole equation, sticking it in there instead. Let's bring that 5 over. So we've got 2 cot squared, 2x, minus 5 cot 2x, minus 2, so plus 2 equals 0. This is just a quadratic. I know you'll probably have calculators to do it. I do not, but it was 2c minus 1 and c plus 2, I want to say. I will double check that very quickly to make sure that's correct. Like if you have the c being cot this time. Yeah, let me just double check that very quickly just to not go forward with something silly. So if we expand out 2c minus 1 and c plus 2, do we get the same thing? No, I don't. This is wrong. Yeah, this is wrong. I've got the plus and minus the wrong way round, I think. That needs to be a minus, that needs to be a plus. Does that change things? If not, I will just do a calculator solve and get the actual answer. Come on. Well, I just expanded myself. The calculator does not want to expand that for some reason. So that's 2c squared, that's good. We'd get negative 4c plus another c. No, this is not right, is it? I need to do something slightly different here. Or have I done something ever so slightly wrong above? There's a negative, isn't it? Looks okay. No. Let me just factorize it very quickly. What have we got? 2x squared minus 5x plus 2. I was very close. What was it? Oh, they're just both negative. Ignore me. Yeah, both negative. Yeah, I had the right ideas. So this is good. What we get then, C, i.e. cot of 2 theta, or 2x, is either a half or it's 2. We don't have a cot button on my calculator, but you might do, but I don't. So I will flip this over. We have tan of 2x, which is a half or 2. I'm flipping them over. So we want to solve them. One thing we can do ever so slightly, 2x, so change this to make it like between minus 180 and positive 180 for 2x. So now when we look at inverse tan of a half, what number do we get out? We're in degrees here, so let's set things up in degrees. Inverse tan of 0.5, I get a number of 26.6. And if I do inverse tan of 2, I get 63.4. There's some, I don't think that's a coincidence. Like, I think they do just add up to 90 when these times to make 1 or something, but don't trust me on that. But that seems correct in like how I'm thinking about it. So that's good. They're the principal values. So what we're going to have is that 2x is equal to both of those, and then any values we can do by adding on 180 or taking away 180 from these, any multiple of that. So if we added on 180, we'd definitely be bigger than 180, so that's not good. But we can take 180 and not be less than negative 180. So let's take 180 from both. So 26.6, take 180, gives us minus 153.4. And then doing the same for the 63.4, we get a number of negative 116.6. They're both for 2x, so halving all of those for the final answers. 13.3, 63.4 divided by 2 is 31.7. 153.4 divided by 2 gives me 76.7. That's a negative one. And then 116.6 divided by 2 is 58.3, but again, negative. Let me double check my answers from yesterday. I have 13.3, 31.7, minus 76.7, minus 58.3. Yep, that looks good. And again, I have whacked these in calculators, and they do give me the same answers I've just got on that sheet. So this is looking good. Let's keep going to number 10. This is when my students were starting to say it became not so fun. The diagram, it didn't come with the diagram here, but I've made one and put it in the thing here didn't have one, but I've made it. So we've got, yeah, the curve is going over here. That's the curve. We have the point over there. We have that curve there. Line L also shows a normal. This doesn't look like a normal because of the way that I've scaled it, but it is a normal, trust me, like it is the normal. Let me go back here and show you. Everything should, yeah, there you go. Like if you make everything on the right scale, I mean, it is a normal. But to make it not just be like a sillily tall diagram, I've stretched out a little bit. But that is a normal curve. But yeah, just stretch it. Doesn't look quite normal. We want to find an equation for L, and then later on we're going to find this area. So we may as well just view it as one big question of just like, okay, let's find this region basically. So to do that, yeah, we need to find L, and then we need to find that actual area. So to find L, let's differentiate. We have in there, we can view it a few ways. You can either view it as like the chain rule, with this being 3x squared plus 4 to the negative half. You can view it as a quotient rule and do it that way around. Many ways that we can do this. I'm going to do quotient rule, I think, today. So we've already done a product rule, it means so I don't want to do another one there. So if we have our u is going to be 7x, u dash will be 7. Our v is going to be that big thing on the bottom, 3x squared plus 4, all to the power of a half. Let's differentiate that. What's going to pop out? We get a half. We get the derivative of this thing, which is going to be 6x. And we get that big bracket again, but that bracket has lost a little bit of itself. So that's good. The actual equation then for by parts is going to be uv minus uv, dashes on the outside. v squared underneath. So let's stick all that together. dy dx is going to be u dash v, so 7 times this thing. What I'm going to do is call this bracket v still. So we're just going to have a lot of v's flying around and they will cancel out, and then later on we'll work with it a bit nicer. So it's going to be 7v on the top, and then 7x times this thing. So 7x times, this is 3x at the front, yeah, so that's 21x squared. And what this thing is, this is 1 on v. So what we have is 21, take away, 21 x squared on v. And this whole thing is over v squared. So what I'm going to do is times the bottom by v. So we're going to have 7v squared take away 21x squared all over v cubed. And from this then, we can expand the v out on the top and start to get some bits, because it's v squared. So what is v squared? Well, v squared is 3x squared plus 4. So 7v squared is 21x squared plus 28. So if I take away 21x squared from that, what do I have? Just 28. So this is the same as 28, like v to the minus 3. But I will write this out as the full. It is 28 over 3x squared to the power of 4 to the power of 3 over 2. Remember, the v itself includes the square root. So this being v cubed is actually the bracket to the power of 3 over 2. That looks good. We want to find the normal when x is 2. So if we plug in x is 2, so dy dx, evaluate x equals 2. But top is obviously 28, and nothing's going on there. The bottom though, what's happening? So 2 squared is 4, times by 3 is 12, plus 4 is 16, square root is 4, cube that is 64. Can we cancel that down? Yeah, we can have a 14 on a 32, and then we can have a 7 on a 16. So that's the gradient of C. That's that gradient. We want the normal curve. So that tells us our actual gradient, the gradient of the normal, is going to be minus 16 on 7. And now we need to find the y coordinate. So if we evaluate y when x is 2, what do we have? 7x is going to be 14. And this is a similar thing. Like this is, again, 2x squared is 4, times the 3 is 12, plus a 4 is 16, square root that is going to be 4. So this is 7 over 2 for the y coordinate. So therefore, the actual equation of this normal, y take away the y value, 7 over 2, is equal to the gradient, minus 16 on 7, times by x, take away the x coordinate of 2. Let's times by a 14 to get rid of that 7 and that 2. So this times by 14 is 14y. This times by 14 is 49. This times by 14 is 32. I'll expand that out, so I have negative 32x. And then I times that by a 2, I'm going to have a positive 64. So times by negative 2, so you get positive. If I collect these together and make it in the form, what do they want? They want all equals 0. So I will have a 14y plus 32x minus 113. Is that? Double check that. 49 plus 64. 113. Is that the same as yesterday? It is exactly the same as yesterday. So that's a good sign. Yeah, very good sign. Yeah, not so nice, but the v squared, leave it as v squared as long as you can, and don't feel like you need to kind of do everything here. You can go away and do figure some bits out and then stick it back in. Don't feel like you need to write v squared in here and expand it in this bit and then do this in one go. You don't need to do that. You can just do some maths over there and then stick it in. It's completely valid. You don't have to do one long chain of maths. You can have 5, 6, 7 little chains, and then all those chains combine together at the end to make the answer. That's fine. So part B, when to intersect the y-axis, so make x 0, 14y minus 113 is 0, so y is going to be 113 over 14. And now then, yeah, find the area. All right, guys, I made a little mistake on that one just with the integration part of it, so I'll walk through this again. We want to find the exact area of R. We've got a few ways we can do this. The way I like to do it is to work out kind of the trapezium. You have this big trapezium with the top one, where we have the gap of it is going to be 2. So the formula will be h over 2, i.e. 2 over 2. And then we want to add together the two heights of it, so this height and this height. This height is what we found in part A, it's the 7 over 2. This height is not 8, be careful, it's not 8, it's what we found in part B, the 113 over 14. It's 7 over 2 plus 113 over 14. That's good, but we need to also take away then the bit we don't want to count, by this bit down the bottom. Because the area we're looking for is between the the curve we have, the normal, and the y-axis. So this little kind of triangle looking bit up there. So that is the integral from 0 to 2 of y dx. So let's look at that individually. What we're going to have, the integral of y itself. Well, what is y? Y is the thing from above, where it's 7x over 3x squared plus 4, all to the power of a half. This is effectively the chain rule. We have to think about like what number is going to come out the front as we do this chain rule. Well, the bottom, you're going to have 3x squared plus 4 will become just 6x, which is very much like that. But we times it by the half, so it's going to be a 3x appears at the top. So really what we want to have is the integral of 3x over 3x squared plus 4 to the half. Because this now, when we differentiate this, what do we get? Let's just look very quickly at the bottom. 3x squared plus 4 to the half. If we differentiate that, a half comes out, 6x comes out, and 3x squared plus 4 comes out. That's the same as 3x with the bracket, and that bracket should have minus a half at the top. And that is, it's the same thing as what we've got in there, exactly the same. So we're able to say then that this integral is correct. We just need to make sure our number out the front is right. So we've factored a 7 out, and we've times by a 3, haven't we? So we need to put a 7/3 out the front of it. So that's looking good. From here then, what we're going to do, we need to plug in those limits of 2 and 0. So if we make that a 2, make that a 0, make that a 2, make that a 0. We can perform the integral. We're going to have 7 over 3, and then we can put those limits of what we found on this other side. So it's going to be just the bracket to the power of a quarter. To the power of a quarter? Sorry, to the power of a half, not power of a quarter. When we plug in those numbers. So 7 on 3. Plugging in the, oh, not a 3, plugging in a 2. See how easy it is to make those little errors? They're always going to happen. You've just got to be very careful of them. So 2 squared is 4, times by 3 is 12, plus a 4 is 16. Square root that, I have a 4. And then similar sort of idea, I'm going to have just a 4 at the end. Square root in that is a 2. So what I have is 14 on 3 for that bit. And now when I stick all these bits together, that one's going to cancel out. I will have 7 over 2 plus 113 on 14 minus that 14 on 3. So let's do that in the calculator. 7 divided by 2 plus 113 on 14 minus 14 on 3 gives me a number of 145 on 21, and that is the same as I got yesterday. Exactly the same. I did something wrong a second ago. I did this as like the I did the chain rule, but I just put a log around it. I don't know why, I just put a log around it a second ago. So yeah, mistakes will happen. Just be careful and things like this. I mean, the answer seems a bit horrendous. Double check it. But yeah, this looks good. And again, I did plot this curve and I did plot the normal. It's hard to obviously work out that area, but I did ask Wolfram Alpha and it said it was correct. So I'm assuming it's correct. Number 11 then, r cos alpha plus theta stuff. So what we can see, r cos, how do you expand that out? Well, you expand it out, well, cos x plus alpha becomes cos cos. So the first term would be r cos x cos alpha. So this is like multiples of cos x. On the left-hand side, we were given just 4. We also know, let's actually move this over a little bit. R is always just going to be the Pythagoras, yeah. 4 squared plus 13 squared, all square rooted. That's 16 plus 169, so 185. All square rooted. So solving this then, we can rearrange and say that alpha is arc cos of 4 on 185. And if we stick that in a calculator, what number does it give us? Make sure you're in radians again. Shift radians, arc cos 4 over root 185. 1.272. Is that the same as yesterday? Yes, it is. That's a good sign. So yep, nice and easy 3 marks for that one. I suppose I would express it. I mean, it's expressed it in that form, so I will still write that down. So 4 cos x minus 13 sin x is equal to root 185 of cos of x plus 1.272. Nice. Now we've got this one for electricity in gigawatts. So it's the same thing as above, yeah? It's the same thing as what I've got up there. So this we can rewrite straight away. D is that 30 at the front wasn't up there, so that's new. Are the coefficients the same? 4 and 13, 4 and 13, lovely. So we just have one R, do you mean we don't have multiple R's? And what's happening inside? So we originally had just x, and that x now is pi t on 12 plus 0.2. So it's going to be cos of that thing, pi t on 12 plus 0.2 plus alpha, so plus another 1.272. We want to find the minimum height, or the minimum demand, whatever it is. This, no matter what's going on in here, all this faff doesn't change the fact that cos is only ever less than 1, or bigger than minus 1, or equal to them, but it's never bigger than 1, do you know what I mean? So minimum, so it's never smaller than minus 1, that's the smallest thing it can be. So this is going to be the smallest possible minus root 185. So our d min is going to be 30 minus the square of 185. The max would be just with the plus in there. When does this happen? Well, what shape is cos? Starts up, goes down, goes back up again. When is it there? At 180. 180 degrees. But there's pi's in there, so it's probably pi. Do you mean? So let's think about that. We want the inside of that bracket, pi t on 12 plus, and I'll make that into 1.472. That needs to equal pi. Let's just rearrange this for t then. Pi minus 1.472. Well, we can have that as one fraction or one little factor, and then times that by 12 over pi. And that should be a value for t. Sticking that in the calculator then, what do we get? 12 over pi, lots of pi minus 1.472. I get a value of 6.37, 6.38, sorry, when you round up. Which is, if we, and again, that should be approximation. What's 0.38 in minutes? Let's take away the 6, times by a 60. I get 23 seconds, minutes, sorry. So it should be like 6:23. This was hours after midnight, so it is like 6:23 a.m. is the minimum, the time when the minimum energy demand is happening. All right, hello again. Another little silly mistake on this one. So they want the rate of increase, like how much per hour is it increasing by, at 3 p.m. So we need to find dt. So differentiating the thing that we got given up here. So as we do that, what's going to happen? The 30 is going to go away. In here, what's going to happen is that this is going to end up timesing out the front, but not with the t. So we're going to have that it's equal to 185 square rooted times by pi on 12. What happens to cos? Becomes negative, negative sign. And the bracket inside will stay the same. So pi t on 12 plus 1.472. So let's plug in the value of 15. Noticing that it said 3 p.m. But it's also said that we are counting from hours from midnight. So 3 p.m. is 15 hours after midnight. So if we plug in that value of 15, we're going to have root 185, the negative of that, times by pi on 12, times by sine of 15 over 12 is 5 over 4 pi plus 1.472. So let's write that in the calculator. Negative square root 185 times by pi on 12 times by sine of 1.25 pi plus 1.472. I get a number of 2.75-ish. So yeah, 2.75 gigawatts is like how much we're gaining per hour, the increase in electricity demand per hour at 3 p.m. Looks good to me. Was that the same as yesterday? Yes, it was. Everything else has been as well. Give a reason why it would not be sensible to use the same equation to model the demand for electricity in the UK on every day of the year. Well, it's not going to be the same every day, is it? You think there are lots of ways you can explain this. In the summer, we're going to use generally less electricity because we're not having the heating on. But it's like we're going out and doing more things, so it might be more. So it's like hard to say which way around it's going to be. We also have things like Christmas Day. I mean, it's going to be a lot more used in households, but a lot less used in businesses. So it's going to be a big fluctuation depending on the temperature, depending on the climate we have, depending on the world situation. Do you know what I mean? Are we able to use electricity as much? Is it costing more? Do we end up using less? Lots of things need to explain it. I would just say that there's no guarantee that the demand for electricity in the UK is the same on every day of the year. That's not guaranteed. It's most likely not true. It'd be very surprising if it was exactly the same every day. So yeah, anything that common sense here should be fine. But I'd say like there's going to be natural variation in demand per day due to climate, due to temperature, due to geopolitical affairs, due to bereavements, due to all sorts of things. Anything you want is valid, basically. Anything that you can think of, why do you use more electricity or less electricity, is always going to be true. Do you mean you've got exams coming up, you revise more, you use more electricity? Simple stuff like that. So we'll keep going. Everything on there looked good. This one was the one I couldn't check because it's all P's and Q's, but I did try and do some bits and it looks fine. Everything looks okay, do you know what I mean? But it's not so easy to check. Just to rewrite that so you can see it a bit nicer. This is y is equal to the modulus of px minus q, where p and q are both positive. We need to sketch this graph. So let's have a big diagram over here. One thing to notice is a modulus with nothing added to it, so it's never going to be negative. It's only ever going to be positive. If we imagine there's no modulus, what would it look like? It would have a y-intercept of minus q and a gradient of p. So it'd be some curve that does this, and that point is like minus q. So all that's going to happen is that at this point we just bounce up now. And we're going to draw this like V, this V bit of it. So let's do that. We'll have this coming down. And we'll have this going back up. They should be the same gradient. Obviously, it's hard for me to do that in the drawing here. They should be the same. Where these bits cross over, well, we said, like, yeah, if we plug in x is 0, what happens? That goes, we have minus q. We do the modulus of it. We knew q was positive, so it's going to turn it back into the positive value of q. Other way around, if we make the actual modulus be 0, then px minus q equals 0. So x is q over p. And they should be the only points where we cross the axes, I think, on here. That looks good to me. We now have a new equation, y equals k over x. Given that c intersects the curve at 3 distinct points, find in terms of p and q the range of values for k. Okay, yeah, it looks horrendous. I mean, as you draw it, it's not too bad. So we have a few options. It's k over x, so it's some reciprocal curve. We don't care about this quadrant, do we, at all? We know k is positive, so we cannot ever be in these quadrants either. So we only care about this one. So let's just draw what we have. K over x is something that does that, yeah? I don't know exactly how it's going to do it. But what we can see, this would be quite a large x. As we lower x down, the graph just ends up coming underneath itself and doing that. So what we get is that it's always crossing this curve, because this curve covers the entire outputs of y's, do you mean? This goes through every single y value. It goes from here and then hits infinity. This one starts from infinity and goes to 0. And they go in opposite directions. So they will cross each other. They are both continuous. This starts at 0, goes to infinity. This starts at infinity, goes to 0. There's no way they can get there without crossing each other. So there's that always going to be one on the kind of like normal part of the curve of the line we have. Then the question becomes whether this green one hits that blue one or not. Because we could take this and move it up and have it not hit it, and then hit it once and hit it twice. We want that boundary point when it hits it once. So we want to take the green line, k over x, when we set it equal to the blue line, but this is the reciprocal part of it, so it's going to be equal to q minus px. We want this to have exactly one solution. So we want the discriminant of this thing to have one solution. If we times everything by x and add things over to the left-hand side, we get px squared minus qx plus k is equal to 0. So Let me just actually mute that if I can. Yeah. We need this to have exactly one spot. We need to have two solutions. So we want the discriminant of this thing to be positive. So that tells us that b squared, i.e. q squared, take away 4 times a, i.e. p, times c, i.e. k, needs to be positive. Rearrange this for k. K is going to be less than q squared on 4p. So basically this is just the quadratic stuff in disguise. It just looks a bit weirder because yeah, it just looks much weirder than it is, but it's effectively finding the number of roots of a quadratic. That's the same as we got yesterday, yeah. Yep, that all looks good to me. Yeah, does look good to me. 13 then, so we're nearly getting there now. Only 2 more to go, I think, or 3 more to go, including this one. So third, fourth, and fifth terms are sine, root 2 cos, and root 3 cot, where theta is a constant and it's between 0 and pi on 2. We want to find the exact common ratio. So they're geometric, so what we have is that the ratio of them is the same as you move along from consecutive terms. So we're going to have that the middle term, the fourth one here, root 2 cos theta, over the third term, sine theta, i.e. how do you go from like 3 to 4? Is the same as if we go from 4 to 5. So that root 2 cos on the bottom and root 3 cot on the top. If we times both sides by the root 2 cos, it will give us 2 cos squared on the left. And remember what cot is, it is going to be cos over sine. So we can actually just cancel out the sine with like the sine on the bottom there and leave that this is just root 3 cot, root 3 cos. This then is another quadratic, so we can factorize out a cos theta. What we have left over, we'll have a 2 cos theta minus root 3 equals 0. So we know therefore that cos theta is either 0 or root 3 on 2. We have that theta is between 0 and 2 pi. So that tells us that cos theta is not 0, which implies theta is the inverse of root 3 on 2. Well, that the calculator is that 30, it's 30, isn't it? Is it 30? Pi on 6. Yeah, pi on 6, 30 degrees. That looks good to me. They actually want the value of the common ratio, so you need to go back through and plug it into these bits. So let's do that quickly. If we do what is cos of pi on 6, well, cos theta we just know is, we just worked out, and it's root 3 on 2. So we can have that this is going to be root 2 times by root 3 on 2, and then the sine, if we do sine of pi on 6, that's a half. I am very much looking at this like left-hand term here, do you mean the one I've written there? Because both of these fractions are r. I could have subbed it into there. Just I'd rather not deal with cot. I'd rather deal with sine instead of cot. Do you mean? So this is good. Those halves cancel out. Root 2 and root 3 makes it root 6. So that is the value for r, and that's the same as I got yesterday, which is all good. This is good then. So hence find in simplest form the exact value of the sum of the first 3 terms of the sequence. So remember, we know theta now. So like these, they look a bit horrible. What actually are they? Well, the sine theta is just a half, and we times by root 6 as we move through. So this being the third term, we want the sum of the first 3. We need to divide by root 6 as we go. So the one before it's going to be 1 over 2 root 6. One before that's 1 over 12. And we just want to add those bits up. So doing that, 1 over 12 plus 1 over 2 root 6 plus 1 over 2. Ooh, be careful on where that's going. I get 7 plus root 6 all over 12. Again, this is not so easy to check. Yeah, not so easy to check, but I have got exactly the same answer I got yesterday. So that's a good sign that things are looking correct. You didn't need to do like imagine like the geometric sequence sum formula thing here. Didn't need to do that. You can always just work it out individually. Like, it still is correct. Sometimes easier with smaller terms to work it out. You could also think of us having like, okay, a is a half, and r is actually like the other way around, 1 over root 6. What we've done, basically what I've done here, doing working backwards for the sequence, and then you've got n is 3 to work it out. It would be exactly the same answer as we've got here. So this is all looking good. Number 14, we've got chemicals in lakes being monitored and stuff. T as monitored begins more by this equation. This is one of the worst ones I've seen in A-level maths. So initially x is 0.3 at t is 4, x is 21. So let's just go and solve this. I mean, 8 marks to do everything. So we got x's, we got t's. X is going on the left. So dx over x. T is on the right. A minus t dt. Integrate both of those bad boys. Left hand side, what is it? It is log. Right hand side, what is it? At minus t squared on 2 plus c. I'm not going to leave that as plus c though. I will eventually at some point want x by itself. So I need to remove logs from things here. So this c, I'm going to call the log of c. Doesn't matter. I could just call this cat. It's okay. I can call it anything I want. I could draw a picture of Mona Lisa if I want to. Anything. It's just a symbol that refers to a constant. This is a constant. Even though like it's log of a constant, that's still a constant, isn't it? So as long as the thing you have is a constant there, doesn't matter what it is. None of these symbols have to be what they are. You can use any symbol you like, as long as it's okay. Like I could swap all of these A's out for, I'm going to have a square instead everywhere. No reason why you have to do letters. Absolutely none at all. You can use any shape you like, as long as it's the same shape you're using. So here, as long as this is a constant, doesn't matter the fact it's log of a constant. I could write constant squared. I could write e to the constant. Anything would be fine. So that's good. We want to plug in our values then. But let's actually first rearrange, I think is the easiest thing to do. So let's take exponentials of both sides. So x will equal to e to the power of that stuff, et, and then we're also going to have minus t squared on 2, and plus the log c. We could write this up here, or we can write this as its own separate e, because add them together, we know that x to the n times by x to the m is equal to the x to the n plus m, and that therefore works in reverse as well. These were added in the powers, so we could write them as just multiples of different bases. Well, same base, but like, you know what I mean, different bits. This one then at the front is just some other constant. What other constant? C. So this is the exact same thing as writing c e to the a t minus t squared on 2. Hence why I've done that. I'd much rather have this just be, now it's just c. Do you know what I mean? Maybe it's horrible to start with, but I don't care about how I start. I care where I end up. And this is much nicer to deal with than having some like e to the c thing flying around. And yeah. This is good then. Let's plug in our values. We have coordinates of 0 and 3/10 and 4 and 21. This entire question, you only need those 3 bits of information. That's it. You need nothing else. Or everything that they're writing down here does not make a difference really at all. Do you know what I mean? Does not make a difference whatsoever. The fact that this is about chemicals, you could just change everything. You have this equation, you have these turning points, then just say find the particular solution. Find max. X equals 0.1, find t. That's it. That's all you need from this page. All the other bits are just faff. And it's like, can you understand that all of this is just faff and we do not care about it? We actually just want to extract these little bits of maths and that's it. So let's do this. Let's plug in our values. If we make t 0, what's going to happen? That's 0, that's 0. Together they are 0. E to the 0 is 1. So this whole side is c. So c will equal x, which is 3/10. Similar thing now for a, but it's not going to be as nice. So when we plug in the 4 and the 21, we're going to have 21 is equal to 3/10. E to the a is what we're trying to find, so it's 4a minus t squared, 16 divided by 2, 8. So let's rearrange this then. Dividing this by the 3 is a 7, times it by the 10 is a 70. So this thing is equal to log 70. And therefore a is going to be equal to the log of 70 plus 8 all over 4. You could write this as like it's 2 plus a quarter log 70 as well. Either way, it's going to be fine. Is that what I get from yesterday? X 3/10 a 1/4 of 8 plus log 70. Lovely. Find the particular solution given your form in this. So always just make sure at the end we are rewriting this. So x is going to equal 3 over 10 e to the power of a times t. So it's this thing times t. So t on 4. I've got the on 4 there, do you mean, with the t. Factor of then log 70 plus 8 Just being careful about the fact that it looks a little bit like it could be just 78, so I'm going to just swap them round, so it's like 8 plus log 70, just to make sure that we know the 70s, the 8's not in the log. You could just do that as well. That's good, but then we need to also take away t squared on 4. So this is the full equation that we get out, and I did double check that this, like, it is, I think I double checked that this is the correct, everything looked good. I've got exactly the same thing again. Exactly the same thing again. So unless I've somehow made the same mistake twice in here that I've just not noticed at all, I think what we've done there is all good. Find the maximum concentration. So to do that, if you think, well, when is the maximum of E, is the maximum of this thing. So really we just want to actually, like, when is that a maximum? So we have T over 4. This, I'm not going to use this. This A is horrendous, yeah? It's horrible. Don't keep writing it everywhere. We want to find when is AT minus T squared on 4. So T squared on 2. Did I do that wrong up above? T squared on 2, T squared on 2. Yeah, that should still be on 2. Sorry about that. See, very easy to make these mistakes. Very, very easy. So, yeah, we want that thing to be a maximum. So we effectively want the derivative of that thing to be 0. As we do that, then what happens? Well, it's going to be A minus T? Yeah, A minus T. So T equals A. This should always happen looking over here. If T is A, this whole bracket is 0, we're no longer changing. We must be at the max or min. So we could see it from that as well, straight away, like when is this equal to 0 is when T is equal to A. But that's good, because now we just want to plug in this thing when T is A. So looking up above, like, what actually is the expression in terms of A? It's that. But we know what the C is. So X is going to be 3/10 E to the AT, but T is A, so that's A squared. Take away a half of A squared. So what's that altogether? Well, 3/10 of E to the, it's a half of A squared. So this is looking good. What we've got here is looking okay. Do we need to plug in some numbers? Yeah, we do. We should know what A is, don't we? Yeah, we know it from above. So what I'd recommend now to actually calculate the calculator, again, not so nice to want to go and type this in, do you mean? In like a way like that. So instead, I'm going to type in just the A part first in my calculator. So make a big fraction with a 4 on the bottom. 8 plus log 70. That's now saved in my calculator as the answer thing. So I just need to do 0.3 e to the power of answer squared on 2. And that gives me a number of 32.6. Which is the same as yesterday. Exactly the same as yesterday. So again, these are looking good. I'm matching myself. Everything seems nice and straightforward. They're not so nice to do. This is an idea that if you try and do this with these bits going in there, it is going to be horrendous and you're going to slip up somewhere because it's not nice, do you mean? Maybe you won't slip up, but you know what I mean? It's much nicer to do with A's. So the actual value for A, I've written it down the answer, and then I've written it down and factorized it. And then I put it in here just to show, like, write the solution, giving them in this form, because they didn't say in terms of A. But I've never actually written it down again. Never used it. At no point do I have this horrible thing flying around in all my equations. Imagine, like, this thing is in every single one of these equations. Down here it's squared, and do you know what I mean? That's going to be horrendous to deal with. So don't do it. You know it's A. Just deal with A, and then at the very end, when you get your answer, then you plug in the value for A. But we don't need to be working with this horrible expression all the way through. We've called it something. It is A. Just call it A instead. When is this equal to 0.1? So we need to set our x equal to 0.1. So it has 0.3 at the front, doesn't it? So the non-c bit is going to equal to a third. So we're going to have e to the at minus t squared on 2 equals 1 on 3. Taking logs of both sides then, we're going to have at minus t squared on 2 is equal to the log of a third, so that's negative log 3. Times element by 2, why not? And make all the t squared positive, so going to the right hand side here. We'll have a t squared, we will have a minus 2at, and we'll have a negative log 9, all equal to 0, as in like 2 log 3 becomes a log 9. And then from here, what we're going to do, I'll complete the square actually, I think might be the easiest way. This is t minus a, isn't it, squared, minus a squared, minus log 9, equals 0. And now then we want to rearrange for t, so I'm going to have a squared plus log 9, all square rooted, and add that onto a. That will be our value for t. We don't need to worry about the negative here. Reason being, a squared plus log 9 is bigger than a squared, yeah? So when I square root this, this thing is bigger than a. So if I tried to take it away, t would be negative. And I'm going to guess up here, they've told me somewhere t is not allowed to be negative. So in the exam, like, don't just assume they'd know that, because they might just think that you've got it wrong. So what I'd always do is just circle and be like, t is greater than 0, therefore only positive. That should be fine, do you know what I mean? You could obviously just write down as well, like, we know that t is greater than or equal to 0, therefore t is only equal to the positive version. Anyway, you want to write down, should be all good. Last question then. Yeah, the proof, obviously can't check the proof. Can't check the proof would be allowed, but what I did seemed to work out for me. So let's have a little gander for it. We've got Pythagoras, so we know that they fit in a right angle triangle, and Euclid's contradiction show they both cannot be odd. So I don't know why they bothered starting. I think just to make it a bit easier for you. I think they've realised they've been so horrible. Maybe they didn't do that in the exam, but like, yeah, it's not such a bad way. So yeah, we have those assumptions they've done. Assumptions that a is 2n plus 1, b is 2n plus 1. They're all even. These are not the same, so they're different numbers. We know a, b, and c are always whole numbers as well. What we're going to do then is just start that left-hand side. So a squared plus b squared, that's going to equal to 2m plus 1 squared plus 2n plus 1 squared. Let's expand that all out. We'll have a 4m squared plus 4m plus 1 plus 4n squared plus 4n plus 1. All of these things are either even, or there's an even amount of them. So let's factorize a 2 out of that. What do I have left over? I've got an m squared, so 2m squared plus 2m plus 2n squared plus 2n plus a 1, i.e. like there's 2 1s there, so half of that is a 1. And this inside thing, I'm going to factorize a 2 out of the first, like all the bits that are 2s. So 2 lots of m squared plus m plus n squared plus n plus 1. So we can write that then. That is, let's just move these all over a little bit. Yeah, we can write that again. This is the same as having 2 times 2k plus 1, where k is equal to the bits inside the bracket. Make some more space for myself. Let's just do a job on it. So k is going to be that whole bit inside the bracket, this whole thing. So what that tells us then, we can write, this is c squared, yeah? This is c squared. That's what it should be. But the thing we've got at the end is an even times an odd. Whenever you have an even, does that fit over there? No, not quite. Whenever you have an even and an odd times together, it doesn't make a square number. It can make a square number. Because if you think about the number you result from, well, no, not necessarily. Okay, let's think very slightly differently here. No, yeah, okay, this is just a 2. It's not an even. That's the slight difference. So one thing to note then, 2 is even. 2 is a factor of 2. That's good. But 2 is not a factor of 2k plus 1. So what that tells us is that b squared plus a squared plus b squared, they are a factor of 2. Oh, sorry, this should be the other way around. 2 is a factor of 2. 2 is a factor of 2. 2 is not a factor of 2k plus 1. So i.e. 2 is even. 2k plus 1 is not even. If this was a 3, it'd be not a multiple of 3, it'd be not a multiple of 4. So what we've shown, yeah, this is good. It's even, but this one's odd. So when you times them together, and not just even, but it's just 2, yeah? So what we have, I don't think we even need that first bit, but what we have is that a squared plus b squared is a multiple of 2, but it's not a multiple of 4. Because we have, like, this is just a 2, and this is odd. So 2 times an odd thing is a multiple of 2, but not a multiple of 4. If we have a square number that is even, it has to be a multiple of 4. Because otherwise, when you went to factorize it into the two parts that are the same, you have 1, 2. Whichever side that 2 goes into, there's not a 2 on the other side to make it an even number. So you have 1 even, 1 odd, which is not square. So this is a multiple of 2, but not a multiple of 4. And therefore, we have that a squared plus b squared cannot equal c squared. It cannot be even. So whether that would be enough, exactly like how I ticked all the boxes for explaining it, like have I done it all thoroughly, I don't know. It might not be exactly what they've done. I've probably written this slightly different to how I wrote it yesterday, but same ideas. We go through, we get an expression to show that c squared has to be an odd times an even, and that even thing is just 2. So actually it's 2 times an odd number. So the factors of it, there's an odd amount of 2's in there. So you cannot split them up evenly so that every factor gets the same amount, because you can't have half a 2 in each one. I think that's all good. Everything seems good. Everything seems spot on. I will show you quickly let's go through the whole thing and just make sure that everything's matching up. So I've got all my kind of like work solutions where I check things. That all looks the same. All looks the same again. Yep, all matches up what we did. Yeah, see, I've done the 2 different colors. Do you mean to see which one we want to use? That is the same. Yep, 15e squared minus 1 on 7. This circle stuff, we got the same stuff out. Do you mean? Everything popping up. Yeah, everything's looking good. Everything's looking good for me. If I have done anything wrong, guys, whack it in the comments, because I'm only a human. Do you know what I mean? There might be some bits I've done wrong, but the method should be correct. It should be the right sort of ideas to do things with. Not so nice paper. It's not maybe the worst in the work. It could have been a little bit worse, but it could definitely be a lot better. It could be a lot nicer. But you got to remember, every single student that walks out of that exam every single year is like, that's the worst exam they've ever done. Because it's not so much the exam itself is harder, it's just the situation you're in is harder than any situation you've been in before. So don't worry too much about it. Try and think like maybe you didn't get the answers out, but did you do the right methods, those sort of things. But focus on bits you weren't too confident on. Get better for those for paper 2. And yeah, good luck. Hopefully it will be okay. Oh, yeah, this is what I did for the last one. Very similar. So we expanded the brackets, do you know what I mean? Collected up again, 2 times somethings, 2 lots of 2k plus 1. Yeah, 2k plus 1 is not, that's not, yeah, this is an odd thing. We need, it's a, yeah, a squared plus b squared is even, but it's not a multiple of 4, so it cannot be that. So I didn't write this bit down. Let me put this bit on the end. What this means as well, this last bit, so we have a contradiction. So therefore 2 is even, or a is even, or b is even. So we just add that to the last page of this one as well. Basically, you need that little conclusion at the end. Do you know what I mean? Yeah, need that little conclusion just at the end for these proofs. But method's still right. Whether they actually tick all the boxes, who knows? But I think it's good. But yeah, hopefully you guys enjoyed. Thank you very much. Anything that was wrong, let me know in the comments below. I will try and do paper 2 as well. Do you know what I mean? I'll do some more things as well before the exams. But yeah, good luck. Thank you very much for watching.